To evaluate Hickey algebra traces at Cauchy-Johnlistic basis elements, we're going to need wiring diagrams and something a little bit more general, which I call a star network. First of all, in the symmetric group, given I less than j, let's define square brackets ij to be the interval from I to j. And let's define S sub that interval to be, we'll call it the reversal indexed by the interval ij to be the permutation with one line notation one up to I minus 1, then j minus 1 down to I, and then j plus 1 up to n. So we have all of the letters I through j reversed and everything else in its right place. So this is more general than, this generalizes the elements that we usually use to generate the symmetric group, because Si is the same thing as the reversal S sub I plus 1. And it's easy to see that the elements Si1J1 and Si2J2 commute if the intervals are disjoint. Because swapping the letters in one interval and swapping them in another interval that doesn't touch the first interval can be done in either order. Now if lambda 1 through lambda r is a partition of n, then the longest element of the Young subgroup capital S lambda is, remember capital S lambda is the subgroup that's isomorphic to the symmetric group on lambda 1 letters, symmetric group on lambda 2 letters, etc. So the longest element of this group in the sense that it has the most inversions is S1 lambda 1 times S lambda 1 plus 1 lambda 1 plus lambda 2, because those are the letters in the second block of this partition we're making of 1 through n. And then the last one, I guess, is going to be n minus lambda r n. Those are the last lambda r letters. So in S9, the longest element of the Young subgroup S3321 is S13, S4, 6, the next 3 letters there, the next 2 letters, S7, 8, and then S9, 9. which has one line notation 3, 2, 1, 6, 5, 4, 8, 7, 9. So all the letters are in backwards order on each of these intervals. Alright, now an important fact about reversals is if we multiply a bunch of reversals that are disjoint, then they commute. Oh, actually, I said that already. Another important fact is that if we multiply a bunch of these that are disjoint, then we end up with a permutation which avoids the patterns 3, 4, 1, 2 and 4, 2, 3, 1. So let's say we have intervals I1, J1 through IR, JR. Let's say these are arranged so that I1 is less than J1, which is less than I2, which is less than J2, etc., up to IR and JR. So they're all, the indices are all in increasing order there. They commute, so it doesn't matter, but this, let's just write them in this way. Then if we take the product of the reversals, then that avoids the patterns 3, 4, 1, 2 and 4, 2, 3, 1. So let's suppose that letters C, D, A, B in W match the pattern 3, 4, 1, 2. Now in the one-line notation we have decreasing subsequence, etc. And every decreasing subsequence consists of letters that are all greater than the letters from the subsequences before it. So that means if we see C and then D, D can't be in the same interval as C. It has to be in a later interval. So D belongs to a later interval than C. But then this letter A, which is smaller than C and D, can't appear to the right of that because all those smaller letters have already appeared. So letter A cannot appear to the right of D. So we can't have this subword of W. Alright, now suppose that D, B, C, A in W matches the pattern 4, 2, 3, 1. So 4 and 2 can be in the same interval. In fact, they have to. Then, so 4 and 2 belong to the same interval. Because after the interval containing 4 ends, or I should say D and B, which aren't exactly 4 and 2. So after the interval containing D ends, all the letters are greater. We won't have a smaller letter left. So B has to appear later than D in that interval. So we have something D minus 1, something D, D minus 1, etc. down to B. They're all in the same interval. But then C is supposed to be a letter which is intermediate in value between B and D. So that means C has to appear in here. It can't appear after B. That's another contradiction. So we can't have anything matching that pattern 4231 in the one-line notation either. So as a corollary, if W equals a product of reversals on non-overlapping intervals, so if these intervals are non-overlapping, then the Kaj-Johnlistic basis element indexed by that product of reversals is just the sum of permutations, well, the sum of T sub V over V less than or equal to W. Alright, now using these reversals, we're going to generalize wiring diagrams. Let's generalize wiring diagrams to star networks. So we'll generalize wiring diagrams, which are concatenations of pictures that look like this, with the x's in different places. We generalize those to star networks. Which are concatenations of pictures that look like this. So we have this star from I to J, which contains all of the things between it, all the things between I and J. And these will possibly, so the concatenations of these may involve intervals which overlap. Alright, so to get an idea of what we can do with star networks, let's recall what we can do with wiring diagrams. So let's recall 3 uses of a wiring diagram G for an expression SI1 through SIR. So first of all, it represents the permutation, which is just the product of those. And then in the picture, assume that each path entering an intersection goes straight across it. The second use is it represents E plus SI1, E plus SI2, etc., up to E plus SIR. So this product in the group algebra. So in the picture, we imagine that we're covering the wiring diagram with all possible path families that cover it. So then E plus SI1 up to E plus SIR equals the sum over pi covering G type of pi. The type of pi is the permutation that describes how the paths are permuted from sources to sinks. Now the third use is it represents TE plus TSI1 up to TE plus TSIR in the Hecke algebra. And then in the picture, we cover the wiring diagram. With all possible path families. And then we sort of weight each by the number of defects using Deodar's rule. So this product then equals a sum of all path families pi covering G, Q to the number of defects of pi times T sub type of pi. So for example, let's use the wiring diagram call this G. And that's the wiring diagram of S1, S2, S1. So if we use this in the sense of I, the first method, then G represents just S1, S2, S1, which is the permutation 3, 2, 1 in one line notation. 1 goes straight through this intersection, straight through that intersection, ends up at 3. 2 goes straight through, ends up at 2, and 3 goes straight through, ends up at 1. And if we use it in the second sense, then G represents E plus S1 times E plus S2 times E plus S1, which we can multiply out, and that is 2E plus 2S1 plus S2 plus S1 S2 plus S2 S1 plus S1 S2 S1. And you can see that there's two paths of type E, because the paths that start at 1 and 2 could either not cross and not cross, or they could cross and cross. Similarly, the paths to make path families of type S1, we could have the path families cross and not cross, or not cross and cross, the two paths starting at 1 and 2. If we use this in the third sense as to represent a Hecke algebra element, so this represents TE plus TS1 times TE plus TS2 times TE plus TS1 in the Hecke algebra, let's say H3. And this ends up being, as we showed in another video, 1 plus Q TE plus 1 plus Q TS1 plus T sub all the other permutations that describe path families covering this. And again, so there's two path families of type E. If they don't cross and don't cross, there's no defect. If they cross and cross again, the second time that they meet, they've crossed an odd number of times, so that contributes to a defect. For the path families of type S1, if they don't cross and then cross, there's no defect. But if they cross first and then meet again, then the second meeting counts as a defect and contributes to Q here. Now, a star network can be used in essentially the same three ways. So first of all, let's let G be the star network corresponding to the product of intervals, corresponding to the sequence of intervals or reversals SI1J1 through SIRJR. So first of all, G can represent just the product SI1J1 through SI2J2 in the symmetric group. And to do this, we say each, so we cover it with one path family. So in the picture, you cover G with one path family in which each path goes straight through each intersection. And then the second way we can use it is G represents the product of Kazhdan-Lustig basis elements indexed by reversals. This is I1J1, it's IRJR, and that's an element of the group algebra. In the picture, we cover G with all possible path families. And then we sum their types. So the product is the sum over all path families pi, which cover G, type of pi. So exactly the same formula as before. In the third sense, G could represent the product of Kazhdan-Lustig basis elements in the Hecke algebra. So the intervals are I1 through I1J1 through IRJR. Again, in the picture, we cover G with all possible path families. And then we weight each with the number of defects. Now we have to be a little careful with defects in a star network. We have to record which pair of paths are meeting. So it could be that one vertex is going to be the home of several different defects. So this means it's going to be a little bit harder to draw than before, because before I could just circle a vertex. If there were only two paths going into that vertex, we know very well which paths are intersecting there after having crossed an odd number of times. But if there are 5 paths going into a vertex, it might be 2 pairs of them that are meeting defectively after having crossed an odd number of times. So circling that vertex is just not going to capture what's going on. So let's do an example. So let's look at a product of 2 stars that have 4 spokes on each side. Alright, so our first use of this star network is to record S14, the reversal S14, times the reversal S25. And we can see what that is by making every path go straight through the intersection it enters. So 1 goes up there, and then down to 3. 2 ends up at 4. 3 goes down here and then up to 5. 4 goes down to 1, and 5 goes down to 2. And in our second use, this is recording the Kaj-Down-Lustig basis element indexed by this reversal times the Kaj-Down-Lustig basis element indexed by that reversal. Which is a sum of all permutations less than or equal to 4, 3, 2, 1, 5 in the Brew order times a sum of all permutations W less than or equal to 1, 5, 4, 3, 2 in the Brew order. Now I won't write all of these out, but I want to point out that this has to be divisible by 6. Because if you think about all the path families that start here and end up there, however scrambled they are, there's 6 different things that could happen between this vertex and that vertex that aren't going to make any difference in terms of the end. 3 paths are going to enter it, and then we can permeate those in any 3 ways, and then we're still free to do anything with those 3 paths over there that we were going to do before if we hadn't permuted them. So the 3 paths that, let's say, cross that part from this vertex to that vertex. Can permute themselves in 3 factorial 6 ways. Without changing the type of the path family. All right, now if we use this in the third way, we're representing the Kaj-Down-Lustig basis element indexed by the same reversals. Well, these should really have a 1 in there so that you know I'm thinking of symmetric group algebra elements. All right, I'm going to put in a Q here so that you know I'm thinking of Hecke algebra elements. So the Kaj-Down-Lustig basis element indexed by the reversal S14 times the one indexed by the reversal S25, which is a sum of TV for V less than or equal to 4, 3, 2, 1, 5 times the sum of TW for W less than or equal to 1, 5, 4, 3, 2. And these permutations again are the permutations that we get by looking at just this reversal or just that reversal. Now I don't want to write out the whole expression. But let's look at let's look at one path family. And its contribution. Well, I'll use the big picture up there and I'll color it in. So let's see, I've got red, green, blue. So let's look at the path family that, let's see, with one path it'll start at 1, and then let's say it takes the upper road inside this part, and then it ends at sink 4. And then let's let the next path take the middle here and then end up at sink 3. And let's let the next path well, actually I wanted the green one to go below in the middle. So green takes the low road, and then blue takes the middle road. And then blue ends up all the way on top. And then I'm running out of colors here, but let me invent a new color. Curly color starts at 4, and then that path goes all the way down here and ends at 1, and then we have normal black path that starts at 5 and ends at 2. So it contributes definitely to T 4, 3, 5, 1, 2. Let's see how many defects this path family has. So there's 3 paths that go through this vertex and that vertex, which could potentially cross and then meet again. So 1 and 2 cross and then they meet again. So the defects at the second vertex are 1 and 2. They cross and then meet again. 1 and 3 cross and then meet again. So it's the red path and the blue. They cross and meet again. And then blue and green do not cross. They meet, but they don't cross. They meet and then meet again. So not 2 and 3. So this point of defects here somehow has to be marked with 2 different path families that have a defect of meeting there, but not with the third possible family. So this path family contributes q squared times t sub 4, 3, 5, 1, 2 to the product if we're going to multiply these two colors down, those 2 basis elements out. The end.